Okay, give me a second. So, hello. I'm going to start now. So we're going to discuss the electrical simulation. So by the way, my name is Claudine. Claudine Papag, application engineer at Texas. So if you have any question, concern, just feel free to raise it along with the discussion. Kindly unmute yourselves. I will take a pause every now and then and try to answer it. So let's proceed. So first, I would like to share with you we are the sole distributor of Matrix, the developer of Matlab and Simulink family of products. So we offer Simulink and where you could do simulation and model-based design. For Matlab, on the other hand, it is inclined in technical computing. So we have 100 products widely used in industry, government, and academic purposes. So for our agenda for today, we're going to discuss with you the introduction to Simulink, introduction to Simscape, and Simscape Electrical, where I will provide you with a short demo at the end. So let's start. So for the Simulink, our highlight are development of Simulink model, key factors that you need to remember in the development phase, also important blocks that you could use. Oops, sorry. So this is an example of modeling and simulation in Simulink. So what we're going to do is that we're going to break the system into process, which will serve as requirements. So this is an application. Then we could connect it to create a system in the model. This is used for simulation and for further analysis. All the process that you have seen here can be supported using MATLAB from modeling, so microcontroller using your hardware device, and then support also the simulation or testing phase as well. All the analysis, then if you connect all the system, you could do as well. Could also have state flow. This is created using state flow. Parameterization is also supported. So this is used in control system design, signaling, and then software in the loop, and then hardware in the loop. So in this presentation, we'll discuss about what you can do with Simulink, how to build model in Simulink. This is cover only in Simulink part. Now to analyze result in Simulink, and then making your Simulink model readable. So earlier, I already showed you, we already discussed about the basic of the Simulink using on-ramp. So now we see how it is being applied and what other process you could do to integrate it. So by the use of Simulink, we could create dynamic system and algorithm. You could do scripting and mathematical representation in terms of block. So for this topic, we're going to create a system for solar panel that maximize the ability to extract more sunlight. So this will be our base discussion, just to show you the problem. And what we are aiming. This is what we want. So the subsystem panel defines the mathematical representation. So this is the subsystem panels. Mathematical representation of its position, while the subsystem per motor here defines the mathematical translation. Then we have the PID here to control the output. So the first thing we need to do is to model the system, defines the panel and the motor in terms of blocks. So we're going to create the algorithm for motor and for the panel. Then the next one is that we apply the PID controller. This is for the system to achieve steady state. And lastly, we could test the design. So the second thing that we're going to do is now building the model or building the Simulink. So we are given an equation that represents the panel and the motor. All we need to do is to translate it into model using Simulink block. So this is how you can access the Simulink to create your model. So you go to the Simulink tab and then go to Simulink and then is it running? So go to Simulink and once it's open, you can access, you could choose the blank model. That's it. So next is go to the library browser. As I mentioned earlier, this contains all the blocks that you could use to create your model. So we have the, just to share with you, we have here the continuous, which defines the analog signal of the equation representing the control system. We have the discrete, representing the step equivalent of this continuous system. And then we have the logic and bits, something that we used earlier in the on-ramp. And then lookup tables. This operation is used for binary values. Math operation is for mathematical approach. We have ports and subsystem. This is used to segregate your process. And then sync to represent the output, either distinct or signals. And then we have source, which is for our input. We use drag and drop approach to access the block from the library browser. So this may also serve as your review. So later on, this will also gonna be used in our Simscape or our electrical simulation topics. So better to give you a brief discussion for this one. So we already introduced the integrator. This is relevant since we are given equation in derivative form. And if we run anything in the integrator, we'll be able to get the integrated value. So the first thing that we are going to define is the position. So this is taken from the library browser. Then copy and paste. Since we are dealing with that double derivative, so we're gonna use the two integrator. So you could do register a specific name on the signal and your specific block as well. So you know this already. And then, of course, we're going to represent P as our constant block. So this is your initial, this is your value for torque. And then we're going to define this part. Then, in case you are defining a known variable, you could instantly define it using this parameter. So this is already all shown on the on-ramp. It's already defining the workspace. And then same principle is applied. You could annotate your model. So it is good for readability of your model, especially if you implement a too large system in one environment. How to analyze the result in Simulink? So this is how we could simulate the model to check the response. We could use scope to see the output of the signal. So once the execution is completed, we could check on with the scope. Could also change the stop time and then do simulation. Of course, you could check the value on your scope. So changing the sign of the torque makes the rotation of the course of the panel change as well. So as you can see, the model is working as expected. So let's go to making Simulink model readable. So this is by applying subsystem to segregate the process. So you can see we could apply here the modeling and then create subsystem. The next one, we need to properly label the model. So this is important. So we can also track what input the system is using. So we apply same procedure in the definition of the motor subsystem. So once the equations are defined and working as expected, we could proceed with the next step. So since it's okay now, see so now we can apply a PID controller to the system. So we could maintain the position of the panel to the movement of the sun. So that's what we are aiming. So we need to reduce the error that it is producing over time or creating over time. So we're going to apply PID to avoid undershoot and overshoot value until we reach the steady state of our system. So we define the sun position and then summation. We add the summation here to represent the error. And so we are applying proportional, integral, and derivative. We have already specified blocks for the PID. This is something that we could modify and calibrate. We could also do parameterization here at PID controller at on. So later on, we'll check on that. So here, we could assign the value of, in case we wanted to just calibrate the proportionality and integral part. So you could do that. And then we could assign value since it serves as our parameter value or our variable. we're going to check the characteristic of our output with our send position. And we have an overshoot here. So what we need to do is to calibrate. So before, just to analyze, we reach the steady state at 6 seconds. So you need to wait 6 seconds before finally the sun and the panel contains the same position. It's something we need to fix. So to do that, we're going to replace our send position with an input defined from our external file. So we're going to define that in the configuration parameter. So we're going to define the parameter value of the input, and since we are not using any blocks that defines position over time, this will access the information in the workspace. Then we define the new time stop in line with the input data. So we just use the the specified time in the materials or in the input data that we use in here. So we have the same timing. So now we already have an overview of how you could do modeling in Simulink, something that you could apply when you going to create your own model. So something also that you need to take note. Uh, Next is we're going to discuss the Simscape. So the introduction of Simulink, it's because we're going to use the same environment with the Simscape. That's why we need the basic part of the Simulink, because it might arise in here as well. Or actually, you could incorporate the blocks in Simulink with the Simscape. So as you go along, you'll learn how. So our focus on the focus of our discussion in here is various physical components that you could use in system modeling and simulation. Also, key factors that you should be familiar with during the development phase. So for Simscape, the key features are it supports more than 10 physical domain. It allows you to use add-on products without purchasing any license anymore. It has custom component with Simscape language. It also has involves commands or functions that you could use to access API. It works below support modeling implementation, integration and testing, and also it supports SQL generation. So Simscape enables you to rapidly create models of physical system within a Simulink environment. So with Simscape, you build physical components model based on physical connection that directly integrates with block diagrams and other modeling paradigms. So you model systems such as electric motors, bridge, rectifiers, hydraulic actuators, and refrigeration system by assembling fundamental components into a schematic diagram. So as shown here in the example, so Simscape add-on products provide more complex component and also analysis capability. Another thing is that Simscape helps you develop control system and test system level performance. You can create custom component model using the Matlab-based Simscape language, which enables text-based authoring of physical modeling components, domains, and libraries. You can parameterize your model using Matlab variable and expression. and design control system for your physical components in Simulink. Also, you could deploy your model, um, and then you could do simulation and hardware in the loop. So for Simscape application, we have hybrid electric vehicle. So in here, Simscape works for integration, design the control, and optimize system level performance. So you see that the output change over time here. Same as shown in Simulink. So same thing is done here. And also the input is changing over time. So it is using an external data. Also, another application is actuation system. Aside from Simscape capability to support different physical components, it also allows you to support SolidWorks. So you could transport your 3D design in the environment. So these are the physical domain that Simscape supports. We have the electrical, the mechanical, the thermal, the hydraulic, the thermal liquid, the two-phase liquid, gas, and moist air. So I'll show you the library of the Simscape. So if you open your model, you go to Simulink tab, and then you be directed in the environment. If you go to the library browser, you can search here the Simscape. And if you open this one, you'll be able to find the foundation library. Actually, just for the foundation library, it comprises already of the electrical, the gas, hydraulic, thermal, magnetic, mechanical, and other bodies. It has already contains the complete system. However, these things in the downside, the driveline, the electrical or fluid multibody, other parts, it contains a much advanced blocks. So let me introduce to you to some of the important blocks that you could find in Simscape. So, so in electrical component, we have the element. So this represents your electrical, basic electrical components. The sensor part is for your acquiring the value of the current and your voltage. And then your source. So this defines the circulating power on your system in different modes. And then you have also the hydraulic. So if we go to hydraulic part, we have here the elements. This contain blocks for fluid flows. Also, we have the sensor part. So we get the pressure and flow rate. And then we have the source. So this contains the ideal source of mechanical and hydraulic energy. And then we have the utilities. So this contains the fluid and flow connection between hydraulic and isothermal. So if we go to the isothermal part, we have here the element. So this contains the block that represents the fluid flow in different conditions. We have the sensor. So to get your liquid properties, and then we have the source. This represents the input flow rate and pressure, while the utility defines the fluid itself. And then let's go to mechanical. So these are the most common blocks that you use or we could use in Simscape. Actually, this is also when it comes to industry, these are the common blocks as well that are being used. So mechanical sensor. So same, we have the mechanical sensor that enables you to get the value of the ideal translation motion, the torque, and force. So we also have multi-body interface. So this allows you to connect bodies in the system. We have the rotational element. So it contains the rotation components that we could apply in our system. So these are the common blocks that you use that we use in Simscapes, especially in the industry. So these are the common things that you could use as well. So Simscape provides mechanical building blocks for representing one-dimensional translation. The variable for these components can be solved simultaneously with other components, so you could connect them. The sensor and actuator blocks for the mechanical component that you connect to more elaborate mechanical models, and it is usually built with Simscape multibody and Simscape driveline. So this is to show you that its library has the basic building blocks of physical components that you can use to create the complete system. So we're just using the basic blocks here, but we're able to create a body or a system already for a specific application. So in here, the 3D and 1D mechanical body is allowed to be connected using this part, using the rotational and translational block. Next is modeling electrical system. So Simscape provides electrical building blocks for representing electrical components and circuits. And if you have a Simscape electrical, you could combine these basic elements to a more complex systems. So we also have here the isothermal liquid domain and blocks. So this is you could model isothermal hydraulic system based on mass and flow rate, and of course also pressure. We also have a function that is supporting the conversion. You could upgrade your hydraulic models to use isothermal liquid blocks. Another thing is that with Simscape, it can automatically convert a hydraulic model to use new isothermal liquid domain. So you could check it in the documentation. You could just type in here this function, and it will give you a lot of information, examples, and functions that is related also to this one. So here, hydraulic to isothermal liquid conversion tool. Um, it can easily upgrade models containing model reference, subsystem reference, and library link. This is just to show you the converted hydraulic to isothermal liquid. So from the process, it were able to keep the model reference subsystem references and custom library links. This also maintains its original file names and provide file list or top level folder to conversion function. So this is just an overview of different types of Simscape. So another is the hydraulic system. So it has the same application or application. It allows you to build blocks with model fundamental using the hydraulic elements and can be combined to create more complex system. So those blocks can be defines the pressure flow relationship for a basic physical effect. This includes fluid compressibility, fluid inertia, and mechanical friction. Take note, to define a fluid, you will like to use in the system, you could use the fluid properties. So block diagram editor features. So visual hint when attempting to connect incompatible physical ports. So actually, the Simulink application also has this capability. So in case you connect two ports that is not really compatible to each other, you will have a red broken dots. So it is an indication that it is not a part that you should connect. And then if you like to connect two port blocks, you can do a drag and drop. So another thing is that physical ports and physical signals um, disappear when they are being connected, as you can see here, and also in here. So if you in case you take the Simscape on ramp, you'll be able to see this parameter as well, or these rules that you could apply in your model creation. But I'll give you already the scope of what you should remember in in the creation of your model using the Simscape blocks. So we have also the physical signal converter. So we have here the filtering and units. So the black icon indicates if filtering is enabled. The output signal unit option, we have inherit. So this is the most safe setting that you could apply on your blocks. Because when you say inherit, it means you're just making the value of the block that is connected from to be the same data type with the block that it is taken from. For example, you use an input with data type of uint8 and then you connected it to another block or an operation and you set the output signal as inherit. It will just recognize the data type that you place on your input and then make it its own. So next, so these are the blocks. So these are common blocks that you could use in all types of components here. So you'll be using these parameters or these blocks always for any kind of blocks from this foundation library of your Simscape. So this is to transport your Simulink in case you use an import block from Simulink and you connecting it to the physical system of Simscape. So you need to use this converter block. Same with this one if you're going to transport the output of your physical system to Simulink, you're gonna use this block. And then software configuration, this is connected to all the Simulink or Simscape blocks or Simscape system in order for you to access the Simulink level or the equation level of that Simscape model that you created. So Simscape for physical modeling. So just an overview or just a review. It supports the following. So support modeling, creation of model. This is a combination of block and schematic diagram to represent your system. The equation enclosed in the schematic diagram can be processed as well. So this is the reason why you could easily obtain information of your system through simulation. So in case we do simulation, we could calculate consistent initial state, could support implicit solver for differential algebraic equation, and also we have fast and real-time simulation. So this is also supported in Simulink. So they have the same capability with the Simscape. So in the analysis portion, it has easy to view of log and plot of any quantity capability. It also, as mentioned earlier, it could support 3D animation of mechanical system. Also, it could support the deployment. It could support C code generation, support also for embedded coder tool. This can generate a fast and efficient automatic codes. So the good thing about this one is that since you're using the solver configuration, the one of the utilities of Simscape, the good thing about that is you will able to access the Simulink level or the equation level of the model, and that's really a good representation of uh, to be accessed by your embedded coder. In case you wanted to code generate using the application embedded coder of Matlab. So now we proceed with Simscape Electrical. So for this one, it is provide components library for modeling and simulating electronics, mechatronics, and electrical power systems. So it is specifically for those applications. So it includes model of semiconductors, motors, and components for applications such as electromechanical actuation, smart grid, renewable energy system. You can use this component to evaluate analog circuit architectures, so develop mechatronic systems, analyze the generation, conversion, transmission, and consumption of electrical power at the grid level. So Simscape Electrical helps you develop control system and test system level performance. You can parameterize your model using Matlab variables and expressions, and design control system and Simulink as well. So the good thing about this one is you can integrate mechanical, hydraulic, thermal, and other physical system. Use incorporating it in your existing model using the electrical components. And also you could deploy models to other simulation environment and including hill systems. So as you can see, Simscape, actually even Simulink shares the same workflow with Simscape Electrical. So this is the ano ba tawag doon? Model-based design workflow actually. So we have the requirements, system, implementation. So if you go in industry or for example in an automotive industry, so this is how their model-based design works. They usually start for requirements and then the system. So this includes a control, mechanical or electrical, but usually they use Simulink and state flow. And then they implement it either in embedded software or just single system. And then you can integrate and test as well. So for application, one of these is electromechanical actuator. So the system tracks speed profile, evaluating thermal effects and assess effect of hardware implementation. Check this definition to the documentation if you want to learn more about this one. Actually, it includes a lot of examples that is related to Simscape, something that you could practice. So these are the Simscape electrical components. So we have semiconductor here, motors, and actuators, op-amps, and logic gates, sensors, and passive device. So we also have generators and motors, transformer lines, and converters, electric drives. So mainly the application of electrical Simscape is very inclined in ECE and EE. So Simscape electrical components model, create exactly what you need using Matlab-based Simscape language. So your component is always has an equivalent equation in the Matlab. And this is something that you could access, or this is something that you run actually when you do simulation in the Simscape. You're simulating the equation of your components. So for semiconductors, it is commonly used for switching, signal amplification, and measurement of power losses. Is a application. For motors, we have translation and rotational actuator for specifying electrical losses and thermal effects. Something that you could use. For sensors, we have digital and analog variation. For electronics, thermal and mechanical sensor. This is used to test effect of sensor damage or failure on the system performance. Oops, sumobra. For op-amps and logic, so it supports behavioral model for fast simulation. It also uses model to perform high-level design. It has a capability to avoid nonlinear effect during normal circuit operation. So these are the application. Lastly, for passive devices, it supports linear and nonlinear device. So it can specify operating limits and tolerances. Also test effect of component failure through fault modeling. So modeling electrical power system with Simscape. So I'll give you a key factor that you should be familiar with on how you could model in electrical power system. So in creating model under power system, we use Power GUI. So if as I shown you earlier, if we just do Simscape, we're just going to use a solver configuration. But right now, there's added implementation or added blocks that we need to use. This is the Power GUI block. So this is required since this is where you could initialize your machines and run the analysis as well. So since we're going to deal with a synchronous machine later on our demo, so I'll introduce you some, what you call it, component. So we have the PV generator. This controls output active power and voltage magnitude. So this is something that will be useful later on. So we have the PQ generator. This controls the output of active power and reactive power. We have the swing bus. This controls the magnitude and phase angle of its terminal voltage. So just for you to be familiarized. So later on, we're gonna use this one. Synchronous and asynchronous machine blocks. This can be either parameterized in SI unit or based on the per unit system. So the base value of this system are the nominal power and voltage of the electrical component. So if you want to check on this one, actually this is included in the documentation. You could just search on getting started with Simscape Electrical, and you could check on other parameters or other information that you could gain some information or knowledge. So sensing physical quantity. So these are the blocks that we use for measurement. So later on, we will explore this one. And then measuring components. So when checking parameter of your model system, we could use block available in here. We could check the impedance measurement. We have the multimeter here. Current measurement, the load flow bus. So we have the three-phase voltage current measurement as well. And then this is recommended for Simscape Electrical. So you need to change the solver into ODE 23TV. So I think we're going now to the demo. So this is the last part. So before we proceed, do you have any question? So do you have any question about the Simulink and the Simscape? So I think none. I'll continue now. So these are the problem. So now for the demo, we have load flow analysis. So we're gonna use the one I mentioned to you earlier, the load flow bus to check on. So this is something that we'll use for the measurement of the demo. So the objective is to initialize and verify quantities in a two-generator system. So we have a volt amp reactive, the generator one parameter. So we have the nominal power, line-to-line voltage and frequency. So if you look at this one, this part, so this is the generator one. And the parameter are already written here. Given the active power, the reactive power, we have the R load that have a 40 active power and 0 reactive power. And then you have the generator 2 that contains a nominal power, line-to-line voltage, and frequency. Here. Oops. Not supposed to run yet. So, what else? Nominal power line. So, you have the delta lagging by 30 degrees. We're going to use the Y delta transformer to create a phase shift. So we're going to use the load flow bus block in a model. to specify the bus location and parameter to solve the load flow. So another thing is that something that to remember, we're gonna use the Power GUI load flow tool to solve the load flow because we need this to transform the system into a Simulink level. So this is how we could do it. So we could access the Power GUI, and then we're going to specify or define the generator that we have. Of course, we need to add what do you call this? Constant block and for the voltage. So this need to be connected to our synchronous machine or to our generator. So we need two generator. We have the generator 1 and the generator 2. So we add three-phase transformer. So if you can just see, I'll just following what is on the problem that I shown you earlier. So we need to connect them both sides, the three-phase transformer. Then we just going to change the name so we could specify the characteristic of the block. We have the generator 1 and generator 2. Then we add a three-phase parallel RLC load. So this is our load 1. And then load 2. We're just following what is in the problem. We're going to change the nominal power, the line-to-line voltage and frequency that is stated in our problem. Are given. Same thing in our generator 2. So the nominal power, line-to-line voltage, and frequency are specified. We're going to add it here as well. Going to modify the inertia, the friction, and the pole pair. The same in our three-phase transformer. So we're going to modify it according to the parameter that is specified in the problem. So we're given a 2,400 and 1,200 winding. So for the voltage, it will also modify for the load and active power. Same in the other one or in the second load. This information or the parameter that I'm specifying is already written in the problem. So as I mentioned earlier, the bus selector to connect it to our scope. Since we need to check on the signal, this is where we're going to do the analysis afterwards or after the simulation is done. So there are a lot of parameters that we could check on, but we're only getting the rotor speed, the active power, and the other one, active power. So as you can see here, it is being connected to our scope. So, of course, we're going to do the same thing on the generator 2 later on. So, After we change so it is specified what generator we are measuring. You could copy this one and just use it for the other part of the generator. So since they have the same parameter, you could just modify the name. So this is the complete representation of your model of our problem. So the next one is we're going to check, or we're going to modify the parameters for the analysis. Yeah. To do that, we need to add the load flow bus. So this is, we're going to use this one to measure the load flow. Apply. Same thing to the other one. So we're just specifying the voltage that runs from generator 1 to our connected bus, load flow bus. And then same thing with the second load flow bus. So we specify the generator type. So are the tools. So we're going to specify here again the active power and the reactive power that our generator is using. So we specify the generator to a swing bus. Right. So same thing. So then we're going to update. As you can see, the value of the power and the voltage is changed. So these are the new values of our generator. With the given parameter that we set on our model, we will able to check. Wait a moment. I'll show you the result of the modifications and settings that we add. So this is the model that we created, and this is the generator 1 output. So we're able to analyze the rotor speed, the active power, responsive active power, and our output of the reactive power for generator 1. The same thing with the generator 2. And as I mentioned, you could change stop time to modify what part of the result you wanted to show for the analysis. Of course, not all information from our graph is needed, or from our signal, from our scope is needed. You could use view to show the legends. This one. So I think that's all. The presentation is quite fast since we already discussed the Simulink in on-ramp. No need to stay with that. So, you have any question or clarification about the discussion? If you want to learn the basic of the Simscape, this is quite advanced. You could start on the Simscape on-ramp, actually. instead of starting with accessing the difficult part, but we have. And the parameter, the only difference between them is that you're using physical components rather than you're using blocks that represents equations. And in order for you to access those in your Simscape, you're going to use a special blocks in its utility. So that's all I think. You have any question, Sir Alexander?
Yes, ma'am.
Uh, what is your question po?
Ma'am, Ms. Claudine, since you have mentioned Simscape, is it possible also that Matlab can be connected externally to other devices?
Uh, like po, you can transport actually. You could transport information from other devices to MATLAB.
So that's, for example, from different languages. How about for other devices, hardware devices, real-time hardware devices? Can it perform interfacing as well?
Ah, yes po. You
Ah,
mean for
yes, yes.
like microcontroller?
Yes, ma'am.
Ah, yes po. We support po. We have an add-on products. Actually, I showed it earlier.
Ma'am,
But we
can
have
you
an
present that as, I was waiting for that add-on product. Can we see a glimpse for just a few seconds of that add-on product, which is incorporated to a microcontroller approach?
yes, sure po. Okay. Just give
Ma'am,
me a
thank you po.
second.
Thank you, Ms. Claudine.
Okay. No problem po. Same. So I'll just share my screen again. So let's open the open give me a second, just open some materials here. So I'll give you an example. This is about Raspberry Pi. Actually, I presented already. Since we have a lot of time, we could run through it actually. So we could open the MATLAB. If you go to here, we could go to the add-ons. So since marami pa naman tayong time, gamitin na lang natin dito. So I already show it to others, but so a support page. My sample is a Raspberry Pi. We have a support package for MATLAB and Simulink. And if you get the support package for MATLAB and Simulink, it's a different interface. MATLAB support package is only for the API layer or the scripting of MATLAB, while the Simulink support package is for the blocks. So it has a blocks already. So all you need to do if you want to use the Raspberry Pi, but we have also a Arduino here. And then you could just, since I already installed it, you could just manage.
The one that you're showing right now, ma'am, are the examples for that specific topic, ma'am.
Yes po, for a specific hardware device, for example, Raspberry Pi. So you could just manage and continue with the process. But if we go to the PowerPoint presentation, so we will add the support package by installation, and then we're going to set up the firmware using the MATLAB environment as well. And then we just need to ping the static IP address in order to do it in MATLAB. Meron ako, this is just an example. I hope you could see clearly. So if you open the Simulink, you'll be able to access the, once you install the support package, you'll be able to access the IO parts of the that particular hardware, and you could just specify an input also using the Simulink block. So this is the sample that you could do to create your model with the hardware device.
Now for the connection. So it doesn't need any
You
device that communicates with the outside world, or you can just simply connect it to a USB, and then just as we mentioned a while ago, you have to do the pinging or IP address thing.
So once you already install the support package for the Raspberry Pi, and then do the firmware setup. Actually, we have the process here. Once you open the installation, you'll be able to there is an instruction actually included, so you can follow that, and you'll be able to install the Raspberry Pi to the Matlab. So it has a connection already. Once you ping it, you ping the IP address. It means that you already connected to the Matlab with the hardware. So you don't need any connection anymore. Just to make sure that you can ping the IP address of the Raspberry Pi using the setup or the firmware setup that we have.
So meaning to say, when you say ping, it can be performed wirelessly or wired, something like that, na?
Yes, as long as it is connected to the power supply.
Galing ah.
Ayan po.
Thank you, ma'am.
Okay.
Ma'am, besides Raspberry Pi, what other hardware devices can we connect with it?
I know Arduino is also has a support package here. Arduino. We have the support package for Arduino hardware, and I think NXP. Some microcontroller or some hardware devices are OEMs. The OEMs itself has their MBD toolbox. This is the support package that you could connect with Matlab, because but it depends. It depends on the hardware device. But NXP has a Matlab toolbox that you need to install. But the add-on products or the support package is coming from them. So sometimes it's not included here in the add-on files.
All right, ma'am. Thank you very much, ma'am.
Okay po. Do you have any question po?
Ma'am, last question.
Sige
So
po.
meaning, if we want to acquire that we need to purchase for a license for that.
I think if you're using Campus wide license, you already have an access to all the applications that Matlab has. So if you have an access to that, actually you need embedded coder in order for you to add a support. I mean, this could be a useful one in order for you to access the or transport your Simulink into C and C++ code, something that your hardware device could recognize.
All right, ma'am. Thank you again.
Okay. So, I think no more questions. Could end the session. So we have much more time. If you have any question, please raise it. I think we could end.
Excuse me, may I have a question?
Sure po. Yes.
Based on the Simulink and from the Scape, does it have external factors that we can view to simulate more accurate scenarios. For example, a simple battery in a motor. Does it shows, for example, heat loss from the motor itself? Thank you.
There's no need to add any components. Actually, if you can model those algorithm or parameter in Simulink or Simscape using those uh, component blocks, you could be able to analyze those things on the software or on the device itself or in the environment. Yun po.
So basically, the external factors like the environment can also be viewed and considered or included in the Simulink.
Yes po. We could add noises through adding signals or input.
Okay, that's all. Thank you very much.
Uh,
Can I ask another question?
sure po.
How about, since you mentioned microcontroller a while ago and other devices, how about in networks? I was browsing it a while ago. I was browsing. I saw some components on the Simulink that can be used in networking. So it can also be used for external connection with other devices.
Deploy it on the cloud. Pwede po.
For
Yes
example,
po.
routers, device. Yeah.
Yes po, pwede. It's allowed. Actually, we have ThinkSpeak.
Uh-huh.
So actually, it's part of the and it's free. You could use it for project, something like that. We have ThinkSpeak. I could share. So
Yes,
this
ma'am.
one.
Please go.
So we have the ThinkSpeak platform. So this is free. Actually, we have a demo here for the ThinkSpeak, something that you could use on. So if you have the device or the hardware that is already installed on the Matlab, you could directly, it has an IoT platform as well that you could use. So this is an example of a ThinkSpeak. So as long as the device can do HTTP get and post requests, you could use this one. And one good thing about this is you could also add MATLAB script using the ThinkSpeak. So by using the ThinkSpeak write and read function alone, and so you can see I use this build and deploy. This is supported by embedded coder already. And you could see that it is implemented in the ThinkSpeak. This is something free that you could work on, especially for the students.
All right, ma'am. That is my last question. Thank you very much again.
Thank you.
All right, Claudine, I think this is the end of the session. There are no other questions left. So again, we
Okay.
would like to thank everyone for attending this session. And I hope, or we hope, that you have gained a lot of insights and knowledge on Miss Claudine's presentation. And also, I would like to thank Engineer Donald for coordinating this to the rest of Bulacan State University's team. And yeah, so thank you all for attending our activities, and we hope we can have more activities soon as well. Thank you and have a good day.
Thank you po.
Thank you so much.